So hi everyone, I'm Rob Taylor. So yeah, I'm kind of going to talk about a big problem that we don't really talk about enough, and AI kind of just makes it a bit worse. Now this is a graph of the amount of data being created each year. This is predicted by IDC a few years ago. And so it's kind of growing faster than exponential, really. The rate of increase of the amount of data being created is exponential. Yeah, so that's okay. We've got clouds and stuff. But there's a bit of a problem there as well. This is kind of, so if you look at processors, as you'll know from your laptops, processors kind of stopped getting any dramatically faster about 2004. We started adding more cores. We've been gradually going up, but adding more cores created a problem. How do you utilize all those cores? So we created things like virtualization and containerization and clouds so that we could use all those cores. And we're kind of getting to the point now where putting more cores on a processor is not really going to be very useful. And we're also getting to the point where just increasing the number of transistors is even getting harder. So what does this look like? So this looks like, if you look at the AMD Intel killer that came out this week, its performance is pretty much exactly the same as the Intel competition. But where they're winning is it's a bit more efficient and it's cheaper. And that's how things are going to go from here on in. So if you're Amazon or Microsoft or a data center provider, you're faced with this problem. People need to process exponentially more data, and you've got to provide the computing resource for this at increasingly decreasing marginal wins. This isn't a good situation. And so there are people who are starting to hit this pain point now, but in a small number of years, this is going to be a pain point for everyone, and especially the sort of people in this room who are doing things that are incredibly compute intensive and data intensive. So the silicon vendors and cloud vendors are experimenting with a number of different ways where we can go from here. GPUs are pretty important in this space. There's some natural limitations there. But the technology that we're working with, and working with Amazon and providers of this technology, is FPGA. Now, who in this room knows what an FPGA is? Well, that's quite good. That's pretty good. I like that. So for those who don't know, FPGAs are kind of an old technology. They've been around since the mid-'80s. And they're what engineers use when they want to simulate building a new chip. So these are things that are incredibly good at doing massively parallel and very dependent parallel problems with lots of I/O and lots of bandwidth across the problem space. And so that makes it if you can use them, incredibly good for doing anything where you've got data in flow and you're analyzing that data or responding to that, or analyzing and then responding to that data. So why don't we all use them already? Right. These amazing things. Look, I can spend a small amount and get 10 times. Why don't we use them already? So the reality there is, currently, to use FPGAs, you pretty much need to be a hardware engineer. Hands up who in this room is a hardware engineer? It's Chris. Oh, this one works for me. And you need to be a pretty good one. You need to have a good few years of experience, and you need to be able to talk to software engineers, and you need to have, the mindset that, 3 years is actually a long project, not a short project. Those who are in the hardware space. So what can we do about this? How can we make this technology available to everyone in the cloud space? And that's what we're doing at reconfigure.io. What we've decided to do is produce a platform as a service, which allows anyone to write the code in Go. And for those who do know Go, it's got some really good concurrency primitives in there. So if you use those to expose the concurrency in your problem, we then use that to utilize on that massively parallel capability of the FPGA. And so this is the developer flow. You write stuff in Go. You have a simple tool. You run it, loads up to the cloud, compiles it, runs it on FPGAs in the code. You get your data back, or you plug it into your microservices ecosystem, or stream your AMQP data in, or your financial logbook data. And there's a lot out there as well in terms of debugging and understanding how this is working and all those sort of hard things. And so one of the questions I often get asked is, what are the main use cases now? Just as I said, the key thing here is problems where you've got lots of data being analyzed. It's data that's been created or in movement. You're analyzing it and you're responding to it. So these are the areas that every time I talk to people, I try and get, what would you use this problem for? So this is what I've collected over the last year or so. There's certainly an awful lot of that sort of cloud monitoring, real-time data analytics sort of problem space where you're getting multiple streams of data. You want to correlate that. You want to do baseline estimation on that. You want to do anomaly detection on that. And that covers for a number of these. There's a lot of potential in the space for doing video analytics and analysis, image recognition. Security in depth, thank you, is a big one. So this is especially doing things like intrusion detection on your network, doing encryption in depth across your data center or your cloud provisioning. And of course, financial is a big area. The financial space is a big historical user of FPGAs in the really high value areas like high frequency trading. And people are starting to look at how to move some of that infrastructure into the cloud. And that's me done, really. So any questions? How was my timing? 2 thumbs.
Any questions?
Well, I'm duty bound to ask this question.
Hi.
Why FPGAs, not custom processors?
Sorry?
Why FPGAs and not custom processors?
So it's a really good question. Why FPGAs and not custom processors? So the biggest thing is really availability. So we see the biggest problem in all of this space is about the programming model. So GPUs finally got used because of the CUDA programming model, the CUDA abstraction made it useful. In terms of doing things outside of that sort of embarrassingly parallel space, the right programming models aren't there. And so half of what we're doing here is bringing the right programming model and giving people the right tools for that. So we think that FPGAs aren't at the beginning of this new world, not the end of this new world, right? So I definitely I've worked with a number of research groups and also with other sort of many core processor guys like Parallella and Taylor people. And we think there's something if we can provide the right access level, then we'll provide a place for people to bring new underlying silicon solutions to that space.
Another question?
So how well does Go map to the FPGA model? Like, are you constraining it or decorating it or what?
Okay, yeah, so you want me to go a bit deep on this. So what we do is we actually convert, so you use the Go routines and channels to expose the parallelism in your problem. We then create an asynchronous data flow graph out of that and then turn that into clock logic. So does that answer the question?
One more?
Oh!
Okay. So so FPGAs, from what I understand, are mostly used for inference rather than training. Is that true? Or are you using for both training and inference?
So in terms of AI on top of platform, I'd be really interested in talking to people who want to start trying to build stuff on top of our platform, right? So, you know, if that's something of interest to you, we have the private alpha available now, and you know, if you've got something very cool you want to build, and we think it's cool too, we'll be able to give you some early access.